Hi everyone. In these videos, I'm going to go through 6 example gas law problems. As part of that, I'm going to explain how to figure out which of the laws to use, what conversions you might need to do, how to solve them using the formulas, and so on. So I'll go through all of that in different videos as I go through the problems. So the first thing I'm going to talk about is very familiar to at least my students because every time we have a problem, I tell you to underline your givens and circle what you're looking for. Your givens are going to be the numbers with the units, and then what you're looking for, you have to read the question. So here we have 4.40 liters, that's one of our givens, of a gas is collected at 50.0 degrees Celsius. What will be its volume? That's what we're looking for. When it cools to 25.0 degrees Celsius. So we have 3 givens here and then one thing that we're looking for. The next thing you want to do is label all of your givens. And this is really important because some of these you end up with a lot of givens. So in order to label the givens, you want to look, let me just find it. Here. Okay, so this is in our document. And the thing that you're going to use to label the givens are the units. That's going to be the easiest way to do it. Sometimes the problem will say, gas is at a pressure of blank, and then that makes it easy. But if it doesn't, like here, it says 4.40 liters of a gas. It doesn't tell you what the variable is. So if you go here and you find the units, liters is volume. Okay, and then the context of the question tells you that this one is going to be V1 because they're saying that's when it started. Okay, so now we get to 50 degrees Celsius. 50 degrees Celsius is a temperature, which you folks know just because degrees Celsius is a temperature. However, if you look here, temperature needs to be in Kelvin for all of the gas laws. Now, you folks learned how to convert from Celsius to Kelvin in probably September, so you might need a little bit of a refresher on that. But all you have to do, it's very, very easy. All you have to do is take this number and add 273 to it. So if you take 50 and add 273, you get 323. So what I usually tell my students to do as soon as they have a gas law problem is cross this out, write the new one, 323 Kelvin, and then label that instead. So this one is going to be T1. Okay, so now we have volume we're looking for, which is V2. And then we have 25.0 degrees Celsius, which we know we need to cross out and do Kelvin. And so that's 298 Kelvin. And that's going to be T2. Okay, so once you've read through the problem, you can go and pick your law. So you have 5 different laws that we're going over on this week's materials. So you have 5 different laws, and it's pretty easy to figure out what law to use if you read the question and take the time to underline your givens and label them. Okay, if you take the time to do that, I mean, what law do we have to use here? Obviously, we have to use Charles's law because we have 2 volumes and 2 temperatures, and we have nothing else. So we have to use Charles's law. So we do Charles's law, V1 over T1 equals V2 over T2. And hopefully you saw from the simulation what that means is that they have a proportional relationship And when you increase the volume, you increase the temperature. Okay, so we have our formula here, okay? Now, what I'm about to say is a little bit controversial among teachers, so your teachers might not be too happy that I'm telling you to do this, but I have found over the years that it is the easiest way for students to solve when there is a fraction. It makes it easier on them if they start off by cross multiplying. So you folks remember cross multiplying, you just multiply across the equal sign. So if we do that, it is V1 times T2. And you don't have to write the times sign, you just put them right next to each other. And then that's V2 times T1. And it just makes it easier. So now you have this formula. We are going to circle what we're looking for in our formula now. We already did it in the problem, but we're going to circle it in the formula. And then think about, how am I going to get V2 alone on one side of the equation? How am I going to solve for V2? So in order to do that, you should see that you would divide by T1 on both sides. So if you divide by T1 on this side, it cancels out. And now you have this new formula that's V2. To make that easier on everyone, I'm just going to erase these because they canceled out. And now it's really easy because all you have to do is take the stuff that you've already labeled and plug it into the right place. Now, one thing I want to say, be careful that you're actually plugging in the right stuff in the right place, okay? Because a lot of kids will get this far and then they just read the problem and they do V1 T1 over T2. You want to make sure you're putting the right stuff that you already labeled in the right place. So V1 is 4.40 liters. And you're going to multiply that by T2. So this is what I'm talking about. Don't just go in order of the problem, T2. And you want to use the T2 in Kelvin. That's why we crossed out the Celsius. So that's going to be 298 Kelvin. And then you're going to divide by T1, which was 323 Kelvin. And then you solve that. So you do 4.40 times 298 divided by 323, and you get 4.06 liters. So the reason it's liters is because the kelvins will cancel the units because there's one on top and one on the bottom, and so you're left with just liters. But you also know that it has to be liters because you're looking for V2, and if you look back on your unit chart or your variable chart, it says that V2 has to be the same unit as V1, so that's how you would know it was liters. How did I know to round at 4.06? Well, that goes back to everyone's favorite, sig figs. This has 3 sig figs, this has 3, this has 3. Since this is multiplication and division, you would take the lowest of the significant figures, which is 3, and so I rounded to this. So this is your final answer. But folks, if you don't remember sig figs, please don't stress out about that. We are going to go pretty easy on you for sig figs, that's for sure. Just round to something that makes sense to you. Okay, so that's this problem. Let's go ahead and do the same thing for this one. Now, one thing I forgot to or didn't mention in the last one is that we also have the ideal gas law that you saw, which has P's and V's and T's, so sometimes it can get confusing. So when you're first labeling all of this stuff, it's pretty easy to tell between these four, the top four, which one you need based on what you have. But sometimes people do get confused about when they need this one versus the combined gas law because they're like, I have pressure, volume, and temperature, and that shows up in both of these things. So the other thing you want to keep in mind when you're deciding between the five laws is look for moles. If moles is anywhere in the problem, then you use the ideal gas law because it's the only one that has moles. So if moles is in any of your givens or it's what you're looking for, you have to pick the ideal gas law. If there's no mention of moles in the question, then you go for one of the other four. Okay, so let's go back to this question. If a gas occupies 3.60 liters at a pressure of 1.00 atm, which is atmosphere, what will be its volume at a pressure of 2.50 atmospheres? Okay, now we go back and we label these. So here we have 3.60 liters. So if you go to your variable chart, which I can never find, here it is, you find liters. Liters is volume, so we're going to label the first one as V1. And then atmospheres. In this question, obviously, it says at a pressure of 1 atmosphere, so that's pressure. But if you didn't have that, you would go here, and we have atmospheres, which I have misspelled right here, so I'll fix that on the doc before you guys get it. There's just no E at the end of it. So this is going to be P1. What will be its volume? V2 at 2.50 atmospheres. So that's going to be P2. So we have no moles in this problem. Okay, so the rule I just talked about was if you have moles, you have to use ideal gas law. That doesn't apply here because we don't have moles here. So that means we're going to use one of the top four, and we have P's and V's, so we will pick Boyle's law. Boyle's law, P1, V1, P2, V2. And this, kids like the best because it's already in a straight line. You don't even need to cross multiply. You just go and solve right from here. So right now we are looking for V2. So I'm going to go ahead and circle that. And then how do we get V2 by itself? We're going to divide by P2. And you have to do that on both sides. And then the P2s will cancel, so you'll end up with just P1 times V1 over P2 equals V2. So I'll go ahead and erase these. And then that's our new formula. So now we go ahead and plug in what we've already labeled. So we have 1 atmosphere, and our V1 is 3.6 liters. over P2, which is 2.5 atmospheres. And then you do that out. So you have 1 times 3.6 divided by 2.5, and you end up with 1.44 atmospheres. I'm sorry, 1.44 liters. The atmospheres will cancel, and you'll end up with liters. Okay. What you also might want to do at the end of one of these problems, especially the ones for the first 3 laws, you can predict what was supposed to happen. Okay, so if we go back to this one, you guys know from the simulations that are in this week and from the stuff you learned last week that if you cool the temperature, what happens to the volume? Okay, you did a lot of work on that on last week and you looked at some of it this week. If you cool the temperature, the volume should go down. Think about the balloon. If you take like a hot balloon outside when it's wintertime, it shrinks. Okay, so you should get a smaller volume. So did we get a smaller volume here? We had 4.4 and then we went to 4.06. Yes, we did. That makes sense. Okay, now if you've got a bigger volume and you stop and think that doesn't make a lot of sense, it's probably because you swapped your temperatures and put them in the wrong place. So go back and check that. So here we have pressure and volume. Now we know pressure and volume have an opposite relationship, meaning that if you increase the pressure, you should decrease the volume. That's one of the things you saw in one of the simulations from this week. So if you increase the pressure, which is what we did here, we went from 1 to 2.5, you should see the volume go down. And we did 3.6 to 1.44. So don't just do the math and move on. Actually stop and think and make sure it's making sense for you. Okay, that's the 2 I'm going to do on this video. I'm going to stop here and start another video.